Our first team presentation is in the area of bioengineering. The students are Argyres, who is from Clayton High School, and Mingu Kim from the David Hickman High School, both in Missouri. Their mentor is Dr. Miriam Rafailovich, Professor of Material Science and Engineering at Stony Brook University. Gentlemen.
Hello, everyone. I'm Aaron Argyres. I go to Clayton High School in St. Louis, Missouri.
Hi, I'm Mingu Kim. I go to Hickman High School in Columbia, Missouri.
And today we'll be telling you a little bit about our project, increasing the proliferation rate and inducing osteogenic differentiation of dental pulp stem cells using graphene polyfluorovinyl pyridine composite substrates. And I know that title's a little bit of a handful, but we'll tell you a little bit more about it, and hopefully you'll understand each piece of the title and how it contributes to the importance of our project.
So our project is largely concerned with the topic of tissue engineering. Tissue engineering is simply the use of a combination of cells, engineering, and materials to replace biological functions. So one major tenet is to be able to find biocompatible, cheap, and effective substrates that we can use to promote cell development in your body.
And one of the ways that we can engineer tissues is by controlling the process of stem cell differentiation. This is the process by which stem cells, or cells that haven't determined which type of cell they're going to become, will change to become a more specialized cell type. And we call these pathways lineages. So when we talk about an osteogenic lineage, that's the process by which a cell becomes a bone cell, or an osteoblast. And we can determine these routes of differentiation through various means. First, different cell types have different differentiation capabilities. So we can choose different cells depending on what we want to get out of them. Secondly, we can dissolve soluble factors into our cell media. These might be steroids or proteins, and these can have effects on the cells and their differentiation lineages. Finally, we can use mechanical cues of the substrates that we actually plate the cells on in order to induce differentiation. And that has certain benefits as far as with soluble factors, you have to put them into the cell media every 3 to 5 days, but if we create a material that is able to induce differentiation, that eliminates that problem.
And so our project, we used dental pulp stem cells. They've been cited to be the most accessible mesenchymal stem cell source. They're simply extracted from your teeth, and they can differentiate into multiple lineages. Mainly, we were focused into osteoblasts, or bone cells. And so they've been a promising tool for bone regeneration because of their high proliferation rate. And so the process in which they osteogenically differentiate is known as biomineralization, which is when phosphate and calcium is deposited onto the substrate. And so we are able to detect whether the cells had undergone biomineralization by detecting a mineral known as hydroxyapatite. So if we're able to detect this mineral, then we know that the cells must have osteogenically differentiated.
So what were the scaffolding materials that we choose to use to induce osteogenic differentiation? We used graphene and polyfluorovinyl pyridine combined in a composite substrate for a few various reasons. First, graphene is a really stiff material. We thought that that might mimic some of the qualities in the body that are close to those bone cells, and that would be a biomimicry, and we'd have that aspect. The polyfluorovinyl pyridine is a hydrophilic polymer, and the nice thing about this hydrophilicity is that it promotes moderate cell spreading. When the cells spread moderately over a hydrophilic polymer like this, it promotes a high proliferation rate, which is really important in the field of regenerative therapy.
So our hypothesis was that if we use graphene, P4BP, and the oxidized form of graphene, graphene oxide P4BP substrates, we predicted that we would see first normal cell morphology of the cells. Obviously, if the cells weren't healthy and dying, it would not be very useful in future applications. We also predicted that there'd be an increased proliferation of the dental pulp stem cells, maybe because of the P4BP. We predicted that there would be osteogenic differentiation that occurred even without these key soluble factors that people use today, like dexamethasone, to promote the cells to turn into osteoblasts. And finally, we predicted that with an increased concentration of graphene and graphene oxide in our substrates, that we would see more osteogenic differentiation.
So we went out into the lab and we decided to first engineer our substrates. And that we had a couple of processes that we decided to use, first being surface intercalation. And what this is that we dissolved our two substrates, polyfluorovinyl pyridine and graphene or graphene oxide, into DMF, dimethylformamide inorganic solvent. We pipetted this material, this liquid onto silicon wafers. We spun cast it and dissolving away the DMF, and we were left with a thin film of our substrate. Then we plated cells on them and counted them at days 3, 5, and 8 to measure a proliferation curve. Finally, we did confocal microscopy to look at the cell morphology and make sure that that was all in check. Then we did SEM microscopy and EDX analysis, and that was able to detect biomineralization so we could get an idea if these cells had undergone osteogenic differentiation. Finally, we used AFM imaging to characterize our substrates and to look at how certain proteins were absorbing into our substrates after soaking them in media.
So these are our results for the confocal microscopy. You can see the pictures taken 3 days, 5 days, and 8 days after the initial plating. This is graphene oxide 5%. And what we found was that first, the cells did show normal cell morphology, and by day 8, these cells are reaching total confluency, which supports our hypothesis that the cells would show normal cell morphology. And these are further supported by our proliferation curve. This is the graphene composite proliferation curve, but the graphene oxide curve is also very similar, almost identical to this one. And what we found was that the cells that were grown on the substrates with P4VP actually showed a statistically significant increase in cell proliferation compared to the normal tissue culture cell plastic. And so we found that the P4VP was the main cause for this raise in proliferation. So after 28 days of our initial plating, then we took scanning electron microscopy images to visually depict the surface of our substrates. And what we found was that there were deposits of hydroxyapatite on our graphene and graphene oxide substrates, even without any dexamethasone that was added, that was not added into the cell media. And we follow that with energy dispersive X-ray imaging analysis. And so we're actually able to identify whether this is hydroxyapatite by empirically determining whether there's a 3:2 ratio of phosphorus and calcium in our substrate. And what we found was, so for the P4VP without any graphene in it, with the dexamethasone, it did osteogenically differentiate, but without any graphene or anything, it wasn't able to osteogenically differentiate. But in our graphene and graphene oxide samples, this is graphene 10%, we found that even in the absence of dexamethasone, these cells were able to biomineralize, deposit this mineral, which means that it must have osteogenically differentiated. And so we were curious about the morphology of our substrates. And so we took atomic force microscopy imaging, and these are our images. And what we found was that first, our graphene particles were relatively uniformly dispersed throughout the surface, as you can see here from our spin casting procedure, but also that the particles seem to be clustered around what appears to be pinkish white blobs on the left. And so we hypothesized using the height analysis that these might be proteins that are present inside the cell media.
So what we saw from those AFM images is that after soaking the substrates in cell media, we had proteins that were clustering around the graphene sheets. And so we thought, how might this affect the osteogenic differentiation? Can we propose a model for how graphene is affecting the osteogenic differentiation of these stem cells? And what we saw is that these proteins that are present in our normal cell media, when we don't have the steroid that's commonly used to promote osteogenic differentiation, we have certain proteins that are available in the cell media, one being fibronectin. Fibronectin has certain hydrophobic regions, and graphene is a really hydrophobic material. So we propose that the hydrophobic regions will have a strong attraction to the graphene and be attracted to the graphene, sticking to it in a certain way, but the hydrophilic sections will be repelled away from the graphene, leaving them to attach to the cells. And in fact, those hydrophilic regions are known as RGD peptide sequences. And those RGD peptide sequences, when they bind to certain integrin receptors on the cells, have been shown previously in multiple experiments to indicate osteogenic differentiation, to induce osteogenic differentiation. So the idea is that these, because of the hydrophobicity of the graphene, we're able to see a model in which the proteins bind to the graphene and certain regions are able to bind to the cell, inducing osteogenic differentiation. So what's there to take away from our project after hearing our results? First is that graphene composite materials can be extremely useful in biomedical applications. We don't need a pure graphene substrate. And the fact is that pure graphene, especially with a one thin film of graphene to make, is very expensive. It's high energy. You need to use chemical vapor deposition, where you heat up the graphene to 900 degrees Celsius, and then you use pressure to create one thin film. But we were able to just dissolve these nanoplatelets into a DMF, and then evaporate it away, and we had a substrate that still performed the purpose that we engineered it to do. So it's a much easier procedure, but also the polyfluorovinyl pyridine that we were able to include in our substrate also had some optimal effects on the cells. Because of its hydrophilicity, we saw moderate cell spreading, and we think that that's the reason that we also saw an increased proliferation rate. And you really want both for the purpose that we want. We want high proliferation rate, but we also need osteogenic differentiation. So how are we going to apply our project? What are the future applications? First is that you could seed these cells into scaffolds for bone regenerative therapy. They could be implanted into the body. And because of the fact that we don't need dexamethasone, you don't need to constantly be replacing the cell media to add these steroids to induce osteogenic differentiation. That role is played entirely by the substrate. But also because we don't need to use the dexamethasone soluble factor, there's this idea that we could create a multi-patterned or a multi-material scaffold, where we have on one side of the scaffold graphene, polyfluorovinyl pyridine, on the other side a different material. And then if we seed cells into that scaffold, they will selectively differentiate but based on the material that they're exposed to. If we have the soluble factor in the scaffold and we have different materials, that factor is going to affect all the cells. But this way we could create a scaffold that affects them in different ways, and we could get some different cell-to-cell interactions that we're able to get from a normal substrate.
And so, of course, all of this work could not be possible without all the support that we have gotten. So we'd first like to thank the Siemens Foundation and George Washington University. We've had such a great experience, and I'm so glad to be here. We'd like to thank our mentor, Dr. Miriam Rafailovich at Stony Brook University. We'd also like to thank Dr. Marcia Simon and Yingji Yu for helping us throughout our project, and of course our family and friends, because they've been leading supporters of us.
Thank you for coming out.